Okay, let's start out with a description of electric current. When we're dealing with circuits, it's important for us to understand the various quantities that are involved in how a circuit can be analyzed and how the energy and some of the other quantities interact in the circuit. One of the primary ones that we deal with is called electric current. Electric current is defined to be the flow of positive charges. The definition is based off of the motion of positive charge. So a arrow representing the flow of current. So if we had an arrow here going to the right here, and we said that that was the current I flowing to the right, that in our mathematics and in our thinking is a positive charge flow, positive charge carriers moving to the right. Now, this definition of current is independent of whether the positive charge carriers are actually doing the moving. In most cases, for example, in metals, typically the negative charge carriers, the electrons, are the ones that are free to move. Now, when a current is represented as a positive direction to the right, that could be exactly equivalent to electron current moving left. So the electron carriers would actually be moving left, but the net effect is a positive charge flow to the right. So theoretically and by definition, we're talking about current in terms of positive charge flow, even if electrons are actually doing the moving. There are a few cases where we will be particularly interested in whether positive charges or negative charges are moving, and we'll see those later. So if current is defined to be the time rate of change of charge or the flow of charge, we represent it by a derivative. I is equal to dq dt. We say that this defines the current. And of course, we can rearrange this by talking about the total amount of charge that would pass a position in a circuit as the integral of dq. And if we solve this equation on our left here for dq, we can see that that would be the integral of I dt. And we would integrate over some amount of time, so we would go from some initial time to some final time. So we can see that the total amount of charge that would pass by a position in a circuit would be the integral of the current flow. This is very similar to like a river. For example, if you had a river with water flowing past, you could talk about the rate of flow of the water. More water flowing past means a higher rate of flow or a higher current, a stronger current. The total amount of water, which we would represent by Q, would be as if, for example, I put a line across the river and I watched how much water flowed through that, section of river over a period of time. So if I watched for a minute, I would get a certain amount of water. If I watched for 2 minutes, I would get a total amount twice as big if the current flow is constant. So those are the interchange between charge and current. And although we learned that a 1 coulomb worth of charge is a very large static charge, 1 coulomb per second of charge flow, which we represent as an amp. So since I is in units of coulombs per time or coulombs per second, we redefine this as an ampere. So 1 ampere represents a charge flow of 1 coulomb per second. 1 ampere is not necessarily an unreasonable amount of current. Typical household circuits are rated at, say, 15 or 20 amps. So a flow of 1 or 2 amps is not unheard of. Unlike in a static charge situation, a static charge of 1 coulomb is extremely large. If we have a section of wire, let's say we have a section of wire that's shaped something like this. It's fat, it gets narrow, and it gets fat again. So there's our section of wire. If we were talking about current flowing, as the current flows here, if this is a current I in this section of the wire, the same amount of current will be flowing in this section of wire, and the same amount of current will be flowing in this section of wire. Current does not depend on the cross-section of flow. The overall effect of the entire wire as it exists in the circuit will determine the maximum amount of current that can flow in that wire, and not a shape of an individual portion. This is different than fluid flow, because fluid flow will actually speed up or slow down based on the constriction point in the wire. So this is a case where electric current is not analogous to a fluid. Um, the the thing to remember, though, is that the current density, which is this new concept, we can declare or define the current density, J, as the current per unit area, or current per by cross-sectional area. So it would be I over A. So here in this section, the current density J would be greater than the current density in area 1. So the current density in section 2 would be greater than the current density in section A, because we have the same amount of current flowing, but it's being compressed into a smaller cross-sectional area. So this concept of current density is useful for uh, for calculating something we call the drift speed. So let's talk about the drift speed. Drift speed is, you can imagine that in this wire that I have above, let's say that I'm talking about these little positive charge carriers. So these are little positive charges. Obviously, the current is telling me that they're moving to the right here. So each of these individual charge carriers must be doing, having a velocity and moving down the wire. And we're all very used to the idea that electricity is extremely fast. I turn on a light switch and the lights overhead turn on immediately. I don't have to worry about these electrons working their way, or positive charge carriers if we're talking about the current, moving from the electric switch in the wall all the way up to the ceiling to turn on my light. But that is not the drift speed. The individual charges themselves move down the wire fairly slowly. Think about walking down an extremely crowded hallway. It's very hard to get from one end of the hallway to the other when the hallway is packed full of people. What happens is you get bumped around as you go down that hallway. Okay, let's look at this hallway, and it's filled with people, and you're the positive charge person here down at the end that's going to walk. Of course, your fastest route would be to walk straight down the middle of the hallway. So if you could follow this path, you could easily move through a hallway that was not crowded. But you can't do that. As soon as you get here, you're going to bang into this person. And in a microscopic level, there's no going around and thing. You're going to bang off there. So you're going to bounce off and kind of end up back that way. Then you're going to bounce off the way this way and kind of go this. So you're going to do a lot of diversion from your path. The thing to remember, there's an electric field in this wire that's generally pushing you down this way. So even if you run into something and bounce backwards, you're going to slow down and turn around and start going the other direction, because you're accelerated by this external electric field being provided by the battery or the other potential difference that's in the circuit. So you will eventually work your way down this wire, and there will be a net current flow dq dt to the right here. But the individual charges take a long time to get down there, and the rate at which they're moving along the wire we refer to as the drift velocity, so v drift. And the drift velocity is closely related to how tightly packed the current is in an area. So it's related to the current density. So we relate the current density to the drift speed by the equation J over NE. So as you can see, so here you can see that the drift speed will go up when the current density goes up. In other words, in a tighter section of a wire, the drift speed does go up. So this is similar to fluid flow. And why is that? If you think about it, the current itself, the rate of flow of charge, has to stay constant, which means that the speed at which charges are moving through, since there's fewer of them per cross-sectional area, they have to pass through the cross-section faster to retain the same number of charges per time passing that point in space. So drift velocity is directly proportional to the current density in a section of the wire. Now this NE N represents the number of charge carriers in a material. So those would be, this N would vary depending on what type of material is carrying the current. So it would be different for copper than from other conductors. And then E is the charge on the charge carrier that's doing the carrying. So here, if we were doing positive charge carriers, then E would be a positive number, and the E would be negative in the case of negative charge carriers doing the moving. This means that the drift velocity would indicate that J has a vector nature, and we can redefine this then as J vector equals NE times the drift velocity vector. So positive charges would drift in the direction of the applied electric field. Negative charges would drift in opposite to the direction of the applied electric field, just like we're used to from electrostatics. And the current then would still be defined in the proper way because the charge here would take care of the positive and negative nature of the drift velocity. Now we know that charge flow is governed or characterized by this current, but if I take a very simple circuit, and if I took, for example, just a battery here, and I took some wires, and I took a wire, and I put it, say, into a light bulb here, and connected these wires to my battery, I should get this light to turn on. So I should get some light out of there, and the question then is, what governs how much current is going to flow around this circuit I, based off of this battery that I've applied here? So the voltage of the battery is driving the current. We call this the electromotive force. The potential difference here establishes a electric field to exist in that conductor. The electric field then will cause charges to move, because we know that a charge placed in an electric field will experience a force. And when the charges move, we call that moving charge current. So there's definitely an interchange here between the applied voltage and the current. It seems entirely logical that if I push harder, if I apply more voltage, that means that the electric field would be greater. The electric field difference between this point and this point in the circuit would be higher. So, so if the voltage goes up, the current must respond by going up. So we would call that a direct proportionality. The voltage is directly proportional to the current. But it's not infinite. If I apply voltage, I don't get an instantaneous flow of current. I get something that limits this. And what limits it is a electrical quantity we call resistance. Resistance is what limits the amount of current flowing for a given voltage. And the relationship actually becomes quite simple. We actually declare the proportionality constant between V and I to be the electrical quantity called resistance. So we say that V is equal to R times I. This is a proportionality constant that makes our direct proportionality turn into an equal sign. And this we call the resistance. This equation, V equals R times I, or more commonly written as V equals IR, is known as Ohm's law. And most things that have resistance behave according to this equation, Ohm's law. And if they do, then we refer to that particular resistance as ohmic. Typical standard resistors that you would use in a science experiment or in a wire would have resistance in your house circuit and things. These are all very ohmic devices. They're not exotic types of things that behave in strange ways. So this equation, this very simple equation, V equals IR, allows you to determine how much current will appear given a circuit's amount of resistance and the voltage that you apply.